I will now tell you how to use the upcrossings to prove Doob's forward convergence theorem. Before I do that, I'd like to remind you and tell you about some notation I'm going to use. So the random variable x is in LP if the expectation of the piece power of the mod is finite. So as usual, this is the piece power of the mod under the expectation and not the other ways around. And the LP norm is just defined to be the piece power of this expectation. The piece root of this expectation. Here p is a real positive real number, so p is bigger than 0. Okay, so that's what it means to be in LP. I'm going to use this notion of them. And let me make another definition here to make everything very clear. If I have a sequence of random variables, xn is a sequence in LP, that just means that each term is in LP. However, if I say that is bounded in LP, what do I mean by that? I mean that if I take the p norms, or equivalently I could also talk about the piece power, then this is of the n of these guys, then this is bounded even if I take the largest of them. So if I take the supremum of the piece norm, that's still bounded. Okay, so there is a uniform bound. An equivalent way of saying that is that there is a uniform bound which bounds all of them for every n at the same time. Okay, so there is a uniform bound, so that same bound holds for each of them, and not this bound is not allowed to depend on n. That has to work for each of them. That's what it means to be bounded in LP. Okay, so let me start off with a corollary of the previous observation we made. So Doob's upcrossing lemma told us that if we have a super martingale, then b minus a times the expectation of the number of upcrossings is bounded by this error correction term, this last term, which is just a one-off term at the end. Okay, so let me start off with a corollary here. The corollary is the following: let x be a super martingale, as it was needed for the upcrossing lemma. Let x be a super martingale, and also let it be bounded in L1. Okay, bounded in L1, just like above. So that means that I have a bound on the expectation of the mod of the xn uniformly for all n, so a bound that works for each of them. Let me actually write this out explicitly. So if I take the supremum of the first norm, which is just the expectation of xn, then this thing, even with a supremum, is finite. Okay? Okay. Fix, as usual, for this business, two numbers, real numbers, a and b, a smaller than b. And so the statement is that in this case, if I look at b minus a times the expected number of upcrossings to infinity, so I don't stop in time, I look at all the upcrossings all the way down to infinite time, that's smaller than or equal to mod of a plus the L1 bound, supremum m e of xm, both of which are finite. In particular, the probability that the number of upcrossings is infinite is 0. Why is that? So why is that in particular part? Well, expectation of the number of upcrossings is finite. Okay, number of upcrossings is a non-negative random variable. It's actually the integer. it could in principle be infinity, but if it was infinite with a positive chance, that would immediately take this expectation to infinity, and that's not the case. So it just can have zero probability of this number being infinite. So almost surely the number of across things is finite. Okay? All right, let's prove this. Let's prove this. And of course I'm going to start off with Doob's acrossing lemma here. Okay, so with this inequality here. And before I do that, I'm going to notice that, well, let's just start off with that. So b minus a times the expected number of across things up to time n of what was our notation? The notation was sorry for that. The notation was ab in here. Okay, so that's bounded from above by the expectation of x n minus a negative part. That was the acrossing lemma. Okay, now notice one interesting bit, that this quantity here, so the negative part is actually one piece of the mod. So this is smaller than or equal, the negative part of anything is smaller than or equal than the mod of that thing. So it's smaller than that, and on that I can apply a triangle inequality, which tells me that I have the expectation of xn mod plus the expectation of a mod, but of course a is not random, so I don't need to care about expectations there. All right, and the thing I want to next make use of is, of course, that these things are finite. So even if I take a supremum of that thing, it's finite. So let me just call this supremum k. I define this to be k, and then this thing is of course smaller than the supremum of all these expectations, which is k plus the mod of a. So I have a bound on the expected number of across things, and notice that this bound at this moment has no n in it, so I can make this bound independent of n. Okay, that's one observation. Here is another crucial observation, and that's the fact that this thing is non-decreasing in n, as a variable of n. It's random, it's a sequence of random variables, okay, indexed by n, but it counts the number of across things, right? Remember, un was defined to be the number of across things until time n, so if I increase n, the number cannot decrease. It's counting something up to n, it's adding new and new counts, so it cannot decrease in n, it can only increase in n. And these are the two crucial ingredients to now do what I want to do. So if it's non-decreasing, then of course it has a limit. It converges as n goes to infinity to a limit, which I'm going to call u infinity of ab. Any non-decreasing sequence will have a limit. This limit is random, so the un's are random. This limit in principle is random, and this limit might at this point be even infinite. Okay, so I need to prove that this is finite and its expectation satisfies the statement of this corollary. Okay, so let's do that. Now if I take my left hand side, so b minus a times the expectation of u infinity of ab, so that's my left hand side here. Okay, u infinity is the limit of the un's, just by definition. Okay, I should have said this here. So u infinity is the limit of the un's, just by definition, the number of across things up to infinity. And since this is non-decreasing, I can use monotone convergence. I can use the monotone convergence theorem to pass the limit of the un's, which u infinity is, the limit of the UNs. This limit here I can pass from inside the expectation to outside the expectation. So this is the same as b minus a. U infinity was the limit of the UNs, and this limit can be swapped with the expectation by the monotone convergence theorem. So the first step I want to make is to bring this limit over from UN, which is U infinity, out to outside the expectation. Okay, the next thing I want to do is apply this line, the previous line, to here, and then I'm done, because then this is smaller than or equal. For every single n, this expectation, b minus a times this expectation, is bounded by k plus a. If it's true for every single n, then it's of course still true in the limit. So this thing will be smaller than or equal to my right hand side, k plus mod a, and that's exactly what this statement was. So at this moment I'm done with proving the theorem, okay, or proving this corollary. All right, so that was a very useful corollary, and now let's see how I can use this to prove. Just adjusting some setup here. Let's see how I can use this to prove the actual convergence theorem for Martingale. Okay, so the statement is the following: Doob's forward convergence theorem, it's called. It's a theorem. So it's called Doob's forward convergence theorem. And it says the following. I start off with a super martingale, and it's bounded in L1. So let X be a super martingale. Again, super martingales are the ones which are non-increasing in conditional expectation. And I also assume it's bounded in L1, just the same way as for the corollary before. Okay, then it does converge. X infinity, defined as the limit of the xn's, exists and is almost surely, exists almost surely, and in that case almost surely finite. Okay, right, so let's see how to prove this. Before we prove it, let me just mention a little trick here. So here's a limit that exists with probability 1, and in some cases you might want to talk about the limit as a sure fact, not only probability 1 but everywhere, everywhere, always. Okay, in that case feel free to define this as a lim sup, and because these limits exist almost surely, then this lim sup, whereas being defined always, almost surely will also be equal to the limit. So if it bothers for you that x infinity is defined only on a probability 1 set, then you feel free to define it as a lim sup, and then with probability 1 it is going to be equal to the limit. Okay, let's do a proof of this, and the proof is quite nice and uses this corollary. So I want to start by contradiction. I want to look at this event that xn does not converge. I want to show that this has probability 0. Okay? At this moment, I don't want to specify where it does not converge to. This convergence might be, this may be to infinity. Convergence to infinity just means that it's growing above every value, and it's not coming back above value. So it's there is a last time that is going to be larger than c for every c. That's what it means to converge to infinity. Okay, so let's assume that this is the case. What does that mean for a sequence not to converge? A sequence doesn't converge exactly, when its lim-inf and lim-sup differ. So lim-inf is strictly smaller than lim-sup. That's exactly what it means not to converge. Okay? Infinitely often we go below some value, and infinitely often we go above some other value. That's what it means not to converge. Okay, now if lim-inf is less than lim-sup, then I can put some numbers in between, some real numbers, okay, which could at this point be, well, just some real numbers, sorry. Now, what I want to do with these real numbers, I can actually choose them, because the rationals are dense in the reals, I can actually choose them to be rationals as well. And you'll see in a moment why that's important. So what I'm going to do now is that I'm going to say that if lim-inf is less than lim-sup, then there is two rational numbers which are different, two different A and B rational numbers, which I can squeeze in between lim-inf and lim-sup. Okay? So union in probability means at least one, right? Or at least some. So lim-inf smaller than lim-sup if there are at least some rational numbers A smaller than B, which can be squeezed in between the two. That's what it means that two numbers are not equal. Okay. Now, if lim-inf and lim-sup are different, what does that mean? Lim-inf means that infinitely often I'm approaching that. Lim-sup means that infinitely often I'm approaching that as well, which means that infinitely often I need to actually go above B and below A. If I don't go above B infinitely often, then the lim-sup would be smaller than that. And if I don't go below A infinitely often, then the lim-sup will be larger than that. The lim-inf would be larger than that. So lim-inf smaller than A, lim-sup larger than B means that infinitely often I have to visit at above B and I have to visit below A, which means that infinitely often I need to do the upcrossing. So that implies that for these A and B rationals, infinitely often I need to do the upcrossing. In other words, U infinity of AB is infinite for these rationals. Okay, again, that's because in order for the lim-inf to be below A, infinitely often I need to visit below A. In order for the lim-sup to be above B, infinitely often I need to visit above B. That means that infinitely often I need to do this upcrossing from A to B. Okay, now these things, according to the corollary we had, the corollary said that each of these things for any A and B, the probability that the number of upcrossings is infinite is 0. So each of these guys have probability 0. These events will almost surely not happen. The probability of each of these things is 0, according to the previous corollary. And I have countably many of them, and this is why I choose rational numbers. I have countably many of these guys. The union of countable 0 probability events is still 0 probability. That's why it was important to do our foundations in measure theory. If you have 0 probability events and you have a countable union of them, then the probabilities can be bounded by the sum of the probability of these 0 probability events, which is still 0. So that means that the probability that xn does not converge is bounded from above by the sum of 0 probability events, which is 0. So we conclude that the probability that xn does not converge is 0. In other words, we did prove at this point that this limit exists almost surely. Okay? The probability that it does converge is 1. Okay, but we still need to prove that the thing is finite. So let's see how we do that. Why is it so we need to prove the second bit here, that the limit is almost surely finite, and for that we just use Fatu's lemma. So I'm going to look at now the expectation of x infinity. What is x infinity? Well, almost surely we have convergence, so almost surely this thing exists. Again, if you're bothered with an almost sure definition without a sure definition, then you can just take the lim sup of the xn's, which is always surely going to be equal to the x infinity, to the limit. Okay, so that's not a big deal. It's defined fine, and since we have almost sure limit, the mods of the xn's will also converge almost surely, and therefore, if you have convergence almost surely, then of course the limit equals to the lim inf. So the xn mod will converge almost surely to the mod of x infinity, and therefore x infinity is almost surely equal to the lim inf of the xn's as well. And here comes Fatu's lemma, which tells us that, okay, xn mod is non-negative, so we can apply Fatu's lemma, and that tells us that the expectation of lim inf is less than or equal to the lim inf of the expectations. Okay, that's Fatu's lemma. All right, and of course the expectation of the xn's have an absolute bound on them. That's due to our assumption of being bounded in L1. So now comes this piece here, is bounded in L1, and therefore the expectation of the xn mods is bounded. It has a uniform bound. There is an absolute k value which bounds each of these guys, which means it bounds the lim inf as well. So this is smaller than or equal to the supremum of the exn's, which is still bounded, it's still finite. Okay, and there you go. You have that x infinity has a finite mean, so it's in L1. Moreover, if it has a finite mean, then almost surely itself must be finite, so it follows. So therefore, x infinity is finite almost surely, because if there was a positive probability of it being infinite, then the expectation of it would be infinite immediately. Alright, so that concludes this proof. The proof is now done. We proved that we have almost sure limit, and we proved that it's almost surely finite. They did that in orange. Okay. And the last thing I want to do in this video is to add a little corollary, or just a remark maybe. I have a remark to add here, and that's the following. So remember that for Doob's forward convergence theorem, I did assume boundedness in L1. The remark is that if xn happens to be non-negative, if my martingale is non-negative, actually it's a super martingale. If xn larger than 0 is a super martingale, okay, so let me just recall how it differs from my assumption up here. So for Doob's forward convergence theorem, I assumed it to be a super martingale, but I didn't say anything about its sign. So it could be positive or negative at this point. I just want it to be a super martingale and bounded in L1. My remark is the following. If it's a super martingale but non-negative, then I don't need the L1 bound. Then, in fact, then the L1 bound is automatic. I don't need to assume that. And here is how it goes. So I'm talking about a super martingale. So I'm going to look at the expectation of mod xn. I need to show you a bound on that that's independent of n. Because it's non-negative, I don't need the mod. Everything is non-negative, so the mod doesn't do anything. And because it's a super martingale, it's non-increasing in conditional expectation, but then it's non-increasing in ordinary expectation either. So this is less than or equal to x naught. And of course it's in L1 because it's a martingale. So this is finite. And x naught acts like this bound k. There is no n dependence, so I can use e of x naught like the bound k. This thing acts like a bound k. I can now put a supremum in front of the whole business. the supremum of Exn mod is still bounded by E of x naught, which is just a fixed number k. Okay, so if I have a non-negative super martingale, I don't need to assume separately boundedness in L1 because that already follows.